Welcome back to Chapter 4. We finished last lecture talking about how to measure the roughness and the International Roughness Index, and today we will be talking more into Chapter 4 regarding the rotting phenomenon and how can we measure rotting and skid resistance. So the question that we need to ask ourselves here is really rotting is considered to be a functional or a structural index? So from one perspective, rotting indicates a structural failure in the hot mix asphalt layers, either the top layer or the base and the subgrade. But on the other hand, rotting also can cause functional failure due to ponding of water into the ruts and potentially also hydroplaning. So you can really say that rotting would fit into both functional as well as structural failure of pavements. So if so, how can we measure rotting depth? So the rot depth really can be measured either manually by sending a technician to the field and try to measure it manually, or in more of an automated way. The manual way is simply using a straight edge. It's simply like a big ruler, and you would lay it on the street and try to measure the amount of rotting, versus the automated way, which we typically use the dipstick, which we already discussed it last lecture. So dipstick can be used to measure roughness as well as rot depth, or you can use profilometer. In fact, the ASTM standards has now a procedure to assess the rot depth using a straight edge. Shifting gears now to the skid resistance, and what do I mean by skid resistance? The way it's really defined in so many standards, the skid resistance is simply any type of resistance to slippage between the pavement and the tire interfaces. So it's really a very critical aspect in the presence of moisture, simply because there will not be that much of interaction between the pavement and the tire, and you would see significant amount of slippage between these two components. So while we're talking about skid resistance, we have to define two different definitions that typically most of engineers would ask and ponder what's the major difference between these two. The very first one is the macro texture versus the micro texture. So the macro texture, as the word says macro, it's really the large scale texture, which is typically represented by the stone particles and surfacing. So if you take a look, for example, at this aggregate here, this aggregate piece, half of it is stuck with the asphalt and the other half is outside or on the surface. So the macro texture is the entire overall texture of the road, which is the total distance from the surface of the road all the way to the height of the aggregate piece. While the micro texture is simply, it's a term given to the finer texture, which can be felt by either running a finger over the surface of the stone particle. For example, you could see here, now look at the same aggregate piece, either this one or this one. The difference now between two components or two surfaces between here and here, if you really go again, touch it by your finger from one piece to the other piece within one aggregate stone, this difference is what we call the micro texture. So now the question is, how can we theorize the skid resistance, and how can we measure it, and if there is different components that comes into it? So several researchers over the years, they try to theorize how to measure friction and the skid resistance. So French in 1989 and Clark in 1981, they came up with this preliminary equation to define what's the amount of total friction between road surface and tire. So as you could see, it's coming from four different components. The first one is the FA, which is adhesion component of friction, and then FH, which is hysteretic or rubber deformation component of friction, which are the very first two are really the most significant components that relates to skid resistance and friction, while the two minor ones are FV and FT. which are the viscous component of friction all the way to the tearing component of friction. So when we talk about friction and skid resistance, we always think of the weather condition. For example, if we are driving in a very dry condition, adhesion friction is by far the greatest component that relates to skid resistance and friction. On the other hand, if we are driving in rainy conditions and now the surface is really wet, especially when we drive on a very smooth or polished aggregate particles, then the adhesion friction virtually drops to zero. So that amount of friction now is not there, and the only contributing factor in a wet condition would be the hysteretic friction, which is gonna provide the driver with a reduced ability to slow the vehicle or maneuver. So again, wet road surface is the critical condition for accidents, simply because the skid resistance will always be measured in wet surface. This is to measure it in the worst case scenario. So whenever we send a technician to the field or with a certain machine to measure skid resistance, we always measure it in a wet condition, in a man-made wet condition, to make sure this is simulating the worst case scenario in the field. So the question now is, what is the adhesion component all about? So the adhesion component really results from the intermolecular attractions, which is more or less chemical bonds between the tread rubber of the tires and the aggregate chips. So speaking of, again, the adhesion component, this is here the phenomena versus the hysteretic or hysteresis component, which we're going to talk about it later on. So as you can see, this is here the rubber element, which is the tire, and those are the aggregate particles, and half of the aggregate are going to be again sticking out from the asphalt surface. And now this interaction, if we really enlarge it and trying to see now the adhesion component, which is basically, as I said, the interaction between the tire surface and the aggregate surface. Now going to the hysteretic component is the other part of the picture here. Basically, this type of component results from the deformation of tread tire as it contacts the macro texture asperities, which is the roughness of the surface. So for example, we typically talk about rubber damping. What do I mean by rubber damping? So not all of the energy absorbed in deforming the rubber is returned when the tread rubber returns again to its undeformed state. And this is actually what I'm quoting here, Clark in 1981. So typically this is going to result into a horizontal component force, which is going to end up acting in the opposite direction to the tire movement. And again, this is what the picture is all about, and I really encourage you try to get more information from this paper here, the publisher Clark in 1981, to give you more insights into this type of analyses. Also in 1975, Moore gave us a conclusion that the hysteretic component is become very small in free rolling wheel rotation, but it's significant for locked wheel braking because of the increased rubber deformation that really occurs when sliding rather than rolling. So from here really can give you an idea that the hysteretic friction would be expected to increase with chip irregularity, as angular chips cause more deformation of the tread rubber than rounded chips. So from a pavement engineer perspective, the way to increase that component of skid resistance is to use more of an irregular chips of aggregates rather than rounded. So if we go, for example, to some of the rivers and try to pick up those aggregate and use them, those are more or less rounded chips, and they will not be able to create that hysteretic component that is very important to have during wet conditions. So in a nutshell here, in a very wet condition, which is the worst case scenario, you have to have very irregular, angular aggregates to resist skid. So going back again to micro versus macro texture. So the micro texture typically help us improve the friction, since sharp peaks can really break through water films, and thus typically it is going to allow some degree of adhesion friction to be restored, while the macro texture, which is again the overall size of the aggregate particle, is going to provide the hysteretic or deformation friction and escape path for water. All what we need really to get rid of the water, so having that irregular shape of aggregate is going to do it. So the escape path is really needed to avoid tire hydroplaning. So what is hydroplaning? Is basically the tire is partially or fully supported by a wedge of water, like what I used to tell you before. While you are driving in a rainy condition, there is really a very thin film of water between the tire and the surface, so you are really driving on very thin film of water. So as speeds increase, for example, some or all the contact with the road will be lost. So partial hydroplaning typically occurs at speeds as low as 60 kilometers per hour. So if you think about 60 kilometers, this is really like around 40 miles per hour, where you start to lose that interaction which you really need between the tire and the surface of the road. This is here more of also an illustration how the skid resistance happen. And let's say this is a tire and the tire is going this way, that means the direction of travel going this way now, and let's say it's a rainy condition. So typically when it comes to skid resistance, we're going to deal with zone 3, zone 2 and zone 1. Zone 1 typically is going to deal more with the water film compared to zone 2 and zone 3. But let's discuss each one of these zones and what's the significance difference between each area. Zone 1, basically it's going to have the first contact with water. Thickness of the water film decreases and typically no friction will be developed. This is zone 1. Zone 2, now it's more or less a transitioning zone where the tire contacts major asperities or the roughness of the surface. So you will see and experience some frictional force will be developed at zone 2. Also at zone 2, since we say it's really there is a balanced zone here, the friction force would be equal to the adhesion plus the hysteresis. So adhesion component, which is going to come from the interfacial shear times the contact area, and the hysteresis component is going to be mainly coming from the dampening losses in rubber as it drapes over asperities or the roughness of the surface. Now zone 3 is really a very completed dry contact area, and the surface indentation filled with deformed rubber and hysteresis present, but the adhesion really dominates. So going back again to the 3 zones, zone 3 is the complete dry area where the adhesion will dominate. Zone 1 is the worst case scenario, there is a thin film of water, and we're hoping to depend on some of the hysteresis that will present in that area. The question here again is skid resistance is always related to speed. So at slow speed, friction is going to be due to adhesion, which is because of the micro texture. At high speed, the contribution is going to be due to the hysteresis become very significant. So those are the two extremes again. If we try to relate them to the zones here, also we can try to relate the skid resistance to the speed. So low speed, the amount of friction that comes at low speed typically from the adhesion, which is we're going to depend on the micro texture, and high speed is going to mainly be coming from the hysteresis component. So skid resistance is really increased by reducing zone 1 and increasing zone 2 and 3. If you think about it, we've got 3 zones, and your goal as a payment engineer to reduce zone 1 as much as possible and increase zones 2 and 3. This is here a very interesting relationship between the skid resistance and the number of traffic and seasonal variations as well. So we could see that skid resistance really deteriorate by increasing traffic until we reach some equilibrium phases. So we got here two lines. The red line here represents at wet conditions in winter time, while the dark blue line would represent the skid resistance at dry summer conditions. So among each one of these two seasons, first of all, we see there is a huge difference between summer season versus winter season. The skid will be much higher at the summertime, where it's a dry condition, there is no wet conditions. So early traffic typically would cause first of all polishing to the aggregate, and once we keep polishing the aggregates are gonna eventually lose contact with asphalt, and they are gonna start to dislocate from the surface of the pavement, and eventually also are gonna see a reorientation of aggregates, which is eventually gonna make the surface very smooth to an extent it's not safe to drive on it, and the skid resistance would be to the minimal values. Also, the tire pressure is very important, and it typically influences the contact area. So for example, at lower pressure, this typically generate a larger area and contact, which typically develop higher friction coefficient. That's why in colder weathers, or in the case of skid resistance that is low, then we would ask the drivers to lower their tire pressure. Also, the wheel load also is a very important factor. Friction coefficient typically increases as the tire load increases. Simply now I'm really increasing the amount of load coming from the truck or the vehicle all the way to the road, and therefore the interaction or the amount of deformation of the rubber tread would be higher, and therefore friction is going to improve. Also, the tire tread itself, it affects the rate of water removal. So if you have a very deep tread, this means there will be the higher friction coefficient, and therefore much better skid resistance, rather than having all tires that the tire tread is going to be very thin. Also, rubber properties is very important. They can impact the hysteresis component of the friction. Softer rubber is going to have a better friction rather than stiff rubber. Softer rubber are going to deform more, and there will be more attraction and more friction between the rubber surface and the road, much more than a very stiff rubber. Also, the vehicle suspension, it typically impacts the load magnitude and the contact pressure, which is eventually will affect the friction of the surface. Other operational factors may also include the speed. So friction really decrease with increasing speed, and we got to know why is this. Also slip. So some slip is necessary to develop friction, as well as temperature. Also temperature is affecting friction. Typically friction is inversely proportional to the temperature. If we increase temperature, friction will go low. If we decrease temperature, friction is going to go high. Water depth, friction is also inversely proportional to the depth of the water, up to 0.005 inches of water. Afterwards, the reaction to water depth is going to be constant. In icy and snowy condition, they typically significantly reduce the friction, and it's not velocity dependent. It's not because we decrease the velocity, it's simply because now the friction between the rubber and the ice, which is generating and covering the surface of the pavement, would be very minimal. When it comes to pavement factors, and this is really what we can work with as pavement engineers, we need to think of the macro and the micro textures of the aggregates. For example, when it comes to macro texture, coarse texture of pavement surface in the range of somewhere between 0.5 millimeters all the way to 50 millimeters would improve the side friction. So I can, as a pavement engineer, I can play with the aggregate size, gradation, binder content, arrangements of aggregates in hot mix asphalt, and I can eventually significantly improve the skid resistance of the pavement. When it comes to Portland cement concrete pavements, typically we will concentrate as pavement engineers onto the macro texture, which is a function of the surface finish and how we're finishing the PCC surface. Also, the micro texture is an aggregate material characteristics. How can I change the aggregates that I use, or how can I change the aggregate source to give me a more rough surface that's gonna have enough amount of skid resistance. One of the bad choices that affect the skid resistance of Portland cement concrete is the use of limestone. Limestone has a very poor micro texture, and it's not really recommended to use it, especially on the top surface of the PCC. This is here an illustrative example for the texture classification. The very first one is a very smooth surface. Going to the second classification here, which is fine textured, but it's rounded. So what does that mean? Meaning that I may use rounded aggregates, and at the same time it's fine textured, while I can use and I can have the same fine texture but using gritty or irregular shapes of aggregates. So again, we can go from smooth to fine texture but using rounded aggregate, all the way to fine textured using gritty or irregular aggregates. Now number 4 would be a coarse textured and rounded aggregates. Now I can have coarse textured, as you can see now the difference between this point and this point from the micro level is much higher than the previous one, but I can still use rounded aggregates. So looking at this classification from the micro perspective, it's not the best, because again it's rounded rather than gritty, but from the macro texture it's good, it's coarse, so the difference between this point and this point is much higher than the previous one. So going now to this one, which I think this is one of the preferred surfaces, is to have a coarse textured and gritty or irregular aggregates. So this is here what I see now. It's coarse texture because again the distance between the highest point and the lowest point of one aggregate particle is high, and at the same time I am using irregular shaped aggregates rather than rounded aggregates. One of the aspects that we also need to think of as a preventive methodology to prevent the road to lose its skid resistance is drainage. We got to know this in the previous chapter, that drainage may affect the entire structure, from the structural performance if the water can get into the system, and we're gonna lose support from the soil and the base and sub-base materials. Also, drainage can be a problem that affect directly the skid resistance. If I have a good drainage system, then I'm gonna be able to provide a good way for the water to escape, which I'm gonna allow better contact between the tire and the pavement, and therefore the skid resistance would be maintained even during rainy conditions. One of the solutions to do that is to use what we call open graded friction coarse materials. Open graded friction coarse material, we would use finer aggregates as well as very big size aggregates, and there will be one side in the middle open or missing. So we're now increasing the permeability of that layer. The top, typically it's the top 1 or 2 inches where you let the water go through it, and then we would make sure the water is gonna be collected from the 2 sides of the pavement once it infiltrates through the top 1 inch or so. So how do we measure the skid resistance? So the skid resistance is measured by an index named skid number. There is an ASTM standards which is E274, and the name or the title for this standard is skid resistance of paved surfaces using a full-scale tire. As you could see here in this picture, we have a vehicle or trailer which is towing this little tire here, and this is how we're gonna measure the friction. We call it the lock wheel led skid tester. So basically here this is the tire. It's a standard tire that we use on the test wheel, and the standardized skid test tire, they have to be tubeless with 7 circumferential grooves, and all of those information regarding the tire configuration has to be defined at the AASHTO M261 or the ASTM E501. That gives you exact standards on how to use those tires. Then we're gonna also need to deliver water. Remember, the worst case scenario that the skid resistance will be really compromised is during a wet conditions. Therefore, while we're trying to measure skid resistance, we have to provide some water ahead of the tire or the test tire to measure friction while the surface of the pavement is wet. So basically we will be applying a static load on the tire. This is the tire which is led by the vehicle. So we're going to apply certain weight. The weight is typically around a little bit more than 1,000 pounds, 1,085 pounds plus or minus 15 pounds. And then what's going to happen is, all of a sudden, while we're applying water and there is weight coming from the tire, now we're going to apply braking system. That braking system is actuated to lock the tire, and now our goal is to start measure some indices to give us an indication what will be the skid number. So once we apply that amount of braking forces, now we're gonna see what will be the torque required to lock the tire, and the skid resistance therefore will be calculated. So the skid resistance, it can be again defined by this simple equation here, which is simply F over W times 100. What is F? F is simply the horizontal force applied to the test tire at the tire pavement contact patch. Basically, you're gonna ask how are we gonna get this force. Is typically calculated from applied torque over the radius, while W is the dynamic vertical load on that test wheel. Once we divide F over W times 100, this can give us an estimate what would be the skid number. So again, we need to keep in mind that the skid resistance is very significantly influenced by 2 factors. The first one is the speed as well as the weather condition. Therefore, when it comes to calculating the skid number, the data must be reported with the appropriate speed, which is most of the time the standard speed is 40 miles per hour. Here more of a schematic to show you how we measure the skid resistance. And for example, the very first picture here, this is the friction tester used by Florida DOT. You could see the vehicle in front, and then we're having the tire here to measure the skid resistance. This is the test wheel, tubeless, and it has certain specs mentioned in the ASTM standards. And now, as you could see here, very interesting, we're having this little instrument that sprays water during the friction test. Once I apply water, and all of a sudden I will apply the braking forces, and then I will take my measurements to determine what will be the skid resistance for that road. Once we do our measurements, the question now is, what are the minimum skid resistance number? So this table here gives you an idea what's the recommended friction numbers for different highway section surfaces as well as different speeds. So here we have first of all the posted speed. If the speed is less or equal than 45 miles per hour versus if the speed is higher than 45 miles per hour. And as you may expect, if the speed of the highway is more than 45 miles per hour, we need to have more skid resistance. We need to have that road is really giving us a good amount of skid resistance, because at higher speed we know that we need more skid resistance of the road to keep the contact between the tires and the surface. If we have speed less than 45 miles per hour, now those are the recommended values for the skid resistance. What is FM40? By the way, FM40 is the skid resistance that was measured at speed of 40 miles per hour. This is the friction number or the skid resistance number at 40 miles per hour. Now we're gonna go now to the three categories here. We're saying questionable, review, and desired. So for example, let's say I have a certain street, let's say the speed was 40 miles per hour, and now this, if I have this number here, friction number equal to 25, this is questionable. That means, again, we need to check and we need to see how can we improve that route to have much more skid resistance than this. This is the review. We need to check and review. This is like a medium stage, while the desired number is 30. So in other words, this table just gives you what's the minimum, medium, and the desired value for friction number or skid resistance number for roads that they are dealing with less than 40 miles per hour in terms of speed, or if you have more than 45 miles per hour. So picking on the second row here, if let's say on highway the 65 miles per hour, which is more than 45, then the desired skid resistance number would be 35. Another concept that we need to discuss here that is related to skid resistance is calculating the stopping distance or the stopping side distance. So there is an ASTM standard which is E445, and the name of the standard is stopping distance on paved surfaces using a passenger vehicle equipped with full-scale tires. Basically, what we need to do here is we would have a regular passenger car with typically the gross weight is smaller than 3,200 pounds, and the tires are ASTM standardized tire with a tire pressure equal to 24 psi, and as I mentioned before, the pavement has to be wet to represent the worst case scenario to measure skid resistance. So basically at the beginning we would drive the vehicle, bring the vehicle to the speed test, and all of a sudden we're gonna apply brakes to promptly lock up all the four wheels and skid, make the car skid until it stops. So what we need to do afterwards, we need to measure the resulting distance, which was required to stop. We call it SD, and then we calculate the stopping side distance number, SDN. So the stopping side distance number is V squared, which is the velocity or the speed of the vehicle at the moment of braking application, over 30 times SD. SD is the stopping distance, and then this has to be multiplied by 100. So there are two equations here, as you can see, one for the British system, and that's why we're gonna here use mile per hour and feet, or if you want to use the metric system, there is another equation for the metric system. So then we need to do some corrections for the speed. For example, if we did the same skid resistance test at the non-standardized test, then we need to do some correction, and the correction can be done using this equation here, which is basically the desired speed minus the speed that the test has to run at, and again you follow the equation to do the correction. Another thing also here that we need to discuss while we're measuring skid resistance is the pavement texture. Pavement texture is really an indicator, and a good indicator to measure the skid resistance. So we talked about macro texture before, and to utilize this concept of macro texture, we need to talk about two different technologies that can be used to measure the roughness and the skid resistance of the road. The very first one is the laser technology versus the sand patch. So let's start talking about the very first technology, which is laser technology. And this machine here is interested to measure the macro texture of the pavement surface. So, which is very similar to what we talked about before. Is similar to the one used in profile measurements, but this one now would take the readings at a much higher frequency and at lower speeds. While the sand patch, which the same thing, it's related to the macro texture. There is an ASTM standard. You can go and find the details more, which is E965. Basically, we're using here certain amount of sand to cover the pavement area, like what you see in this picture. And then the smaller the area, the higher the texture. So I know that there is a certain amount of area, a certain amount of sand that I need to use, and I pour it into the surface of the pavement, and then I have to spread it on certain area and with certain depth. And then the smaller the area, again the higher the texture, because it takes much more sand to fill those texture, and that's why a smaller area would give an indication that there is lots of texture on the surface of the pavement. Based on the sand patch, we're gonna continue in it, and now we're gonna be able to measure what we call MTD, the mean texture depth. So the mean texture depth of pavement macro texture can be measured following this equation here, which is 4V over pi d squared. So what's V here? V is the volume of the sample material used, which is constant. We know by the ASTM standard there must be a certain volume of the sand that need to be used, and then D would be the average diameter of the area covered by the material. So once I know the average diameter, then I can get the area, and then this is more or less than area, and then 4 over 4V times pi d squared. This is going to give you an indication what would be the mean texture depth. And as I mentioned before, larger aggregate particles protruding above the pavement surface is gonna indicate that high MTD and high texture of the surface. This is here the skid resistance survey frequency, and the question here is how long do we need to rely on old data, and how frequent do we need to go to the field and measure the skid resistance. So skid resistance basically of pavements should be measured more than frequently on heavier traffic highways. Why? Simply because once I have more traffic highways, then this is gonna decrease the skid resistance of the road much quicker compared to some roads that we do not deal with so much traffic on them. So for example, here I'm giving you this table here for airports, because airports is even more critical. The skid resistance is more critical while braking and trying to stop the plane during landing, and that's why we have to come up with a criteria. So this is here the table to show you the skid resistance survey frequency on airports. So, and it's all related to the number of jets landing daily. So for example, if you have a very busy airport that has more than 700 jets landing on a daily basis, then this is gonna trigger more frequent skid resistance measurement more than an airport that has less than 50 jets landing every day. So for example, less than 50, that would be similar to our Tyler Pounds regional airport, versus maybe Dallas Fort Worth is gonna be towards the other extreme. So basically that's the first condition to keep in mind, the number of jets, or the how much traffic that every airport is going to have, and also the surface treatment itself. Is the surface is ungrooved pavement, or no surface treatment, or is it grooved pavement or friction course? So if I have grooved pavement or the surface is really friction coarse materials, then the frequency is going to be less, simply because I know I have enough texture and the surface is grooved, so the skid resistance is going to be maintained much longer compared to if I have ungrooved pavement or no surface treatment. Then this is going to trigger more frequent skid resistance measurements. So again, as a little revision here, how to maintain high macro texture and micro texture from the pavement engineer perspective. First of all, we need to have a good crushed aggregate. In the same time, we need to have a tough aggregate, which is unpolished. This is also from the pavement perspective. Also, having in mind that we need to eliminate rutting. This also improves the skid resistance, as well as thinking all the time of having a good permeability. We need to get rid of the water from the surface of the pavement, and the only way, or one of the few ways to do it, is to have an open graded friction coarse materials, meaning that the top 1 or 2 inches are gonna have open graded aggregate. That means I'm gonna have bigger sizes and very small sizes, and the medium size is missing to let the water in the pavement top layer, and then we're gonna get rid of it through the drainage system. Also, we need to make sure we need to eliminate bleeding. So the way to eliminate the bleeding is having a good mix design, appropriate air voids and appropriate binder content, so that at high temperatures the binder is gonna have time and it's gonna have space to go through the air voids and fill the air voids rather than going all the way to the surface. Because again, if I have a problem of bleeding on the surface of the pavement, this is going to affect significantly the skid resistance of the road. So the question here is, okay, how can we restore skid resistance? We know how to measure it. We know that there are several aspects to it in terms of micro and macro textures. Assume now I have a problem, how can I restore it? One of the issues here, we can use seal coat as an improvements for the pavement surface, or I can use open graded friction course, or if the skid resistance has high extent and high severity on a longer sections, then I have to go to the third option, which is the most expensive here, but sometimes we have to go to a 2 to 4 inches overlay to restore the skid resistance of the entire surface of the pavement. Now, the other question here is, how about rough surface finish? How can I do that? So, especially when it comes to Portland semi-concrete, we're gonna use wire or Bristol brooming. This is to improve the skid resistance of the surface. While when it comes to microtexture, is always controlled by fine aggregate. So microtexture is always again fine aggregate. So to improve the microtexture rather than macro, we need to have tough fine aggregates, good resistance to wear. Also have to keep in mind we have to have the right mix design, and lastly, do not over finish. Sometimes we, especially when it comes to concrete pavements, we have a very smooth surfaces. We think this is the best road because it's very smooth, but also we should think of having a skid resistance, a balance between skid resistance and roughness. So keeping those two in mind will improve the microtexture of the PCC roads. Other techniques to restore skid resistance, especially for PCC, but also we can do it for hot mix asphalt, is grooving as well as sandblasting all the way to seal coat. With that, we reach the end of the chapter, and next time we will be talking about the structural performance. So far we finished the functional performance, including skid resistance, roughness, and all the details related to it, and now we're going to move to the structural performance of hot mix asphalt as well as PCC pavements. Thank you.